Hello everyone. In this video I will be solving some example on the true stress true strain so you can have more understanding how to deal with the example of plastic deformation or plastic zone. Now I'm gonna solve 6.43. Now let's see what's given and how we're dealing with the information given to us. For some metal alloy, a true stress of 415 megapascal produces a plastic true strain 0.475. Now, we said that since it's talking about true stress, true strain, we know that we are in a plastic zone. If it just says stress, for example, it says that a stress of 415 megapascal produces a strain of 0.475, you have to know whether it's in the elastic zone or plastic zone. But since it said true here, we know it's plastic zone. Now this is a given case. This is a given case. The question says how much will a specimen of this material elongate? Now elongate means delta L. Why? Because changing the length. Remember, we assume that the material will be pulled in its length. So elongation happens when you have a tension force. So how much this material, this specimen of this metal is going to elongate, delta L, how much it is. But remember, delta L must be related to something, yes? So we say when a true stress 325 megapascal is applied. So we want to understand, we want to find this stress, this true stress 325 megapascal, how much does make a deformation on this specimen? Now we need some information, yes? If the original length is 300 millimeters, so we know the L0 original length. Why? Because in order to calculate delta L, we need the original length of the specimen. 300 millimeter, have it there. Assume value of 0.25 for a strain hardening exponent n. So n value also given to me to be 0.25. Now, I don't want you to look at the solution. I know the solution is just two-step, but how do we find the solution for this example? Now remember, it will ask me for delta L. Delta L related to strain. And I have to find the corresponding strain for this true strain. And it will be a true strain for this true stress. Because we want to find elongation for this stress. So this stress here, 325 megapascal, is going to produce a true strain. And if you remember, we said the relation between the true stress, and true strain, it is through K and N. So if I have the true stress, I have the true stress. Now I have the N as well, which basically is supposed to be this one. So the N, I have it. K, I don't have it. And I want to find ET. Why? Because we want to find elongation under this stress. This stress will produce this strain, and this strain will give me the delta L. So if I want to find, I have to look, I'm looking for this guy. I want to find this one. Strain T in this equation where I have to put 325 megapascal here, K, which I don't know what, N, it's 0.25. Now you remember we said that K and N are constant for a material. So if you have a case, for example here I have N, in order to find K, I need a case which true stress and true strain known. And that's going to be the first in given information. So the first given information, he says that a true stress of 450 megapascal will produce a true strain of 4.475. I can use those two to find K. Why? Because K and N are constants. So if I have, remember, do not mix them. I've seen students, they use this one with this. This is, I always say that a true stress has a corresponding true strain. So always make a table for yourself to know that you're not mixing things. So if this is case, for example, if this is sigma and this is strain. So write it like this. This is 415. The corresponding is 0.475. So you know that this, if this one case is given here, there is another case is given. That case I have what? 325, but I don't know this one here. So I cannot use this with this one. I have to use them the way that it is. So this one with this I can use. Why? Because they are corresponding to each other. They are related to each other. Then I'm going to use those two. As you can see it here, this will be rearranged. It will be sigma t over this one. Now we're going to use the first case to find k. Why? Because k is constant. If I have two values, but remember when I say two value corresponding or related two values, sigma t and strain t, which is true stress, and it is, when I say true stress, it is true strain. So this is for this. That's why we're using 415 with 0.475, and the n is, we know it, n is constant. We found k to be 500 megapascal. Now I can bring this k inside here. Then I have the three value. This time we're going to use the second case. We're going to find a true strain for a true stress 325 megapascal. So we're going to use this equation again, rewriting the same equation, but this time we're going to use the 325 megapascal. So in that case, 325 megapascal, or rearrangement here, you'll be able to do it by yourself. This is rearrangement. I mean, this is the n here. Remember, this k goes under here, then you take root over it, the root on n. Thus there will be 1 over n is, instead of this one, means root n. So, and here you have the values. We'll place it there, and you find a true strain. Now this true strain, we know that true strain is equal to ln, the instant length over the original length. No need to change this one. I've seen students, they change this one. I showed to you in the previous example that in the lesson, I told you can convert this one to, by using this equation, ET is equal to ln 1 plus engineering strain. So I can write engineering strain. Yeah, some students, they will find engineering strain, then they will say engineering strain is equal to delta L over L. That's also possible. But remember, you can directly find it from the true strain. Why? Because true strain is equal to ln instant length over initial length. But remember, you're not finding delta L directly. You will find the which is the instant or the final length, and or the length under this stress. When we call instant length, it means the length of the specimen under 325 megapascal. Now from here, if I just write it down, so it's going to be something like this, will be 0.179 is equal to ln, a parenthesis, we have it here, Li over, we have the original length to be 300. So we said in order to get rid of the ln, we will take exponential. Already we'll multiply both sides with exponential. Then we say exponential of this one times 300 is going to be the Li. Right? Because exponential goes here, exponential with the ln, you're going to cancel each other. Then exponential of this value times 300 will be Li. So I can write it here, Li. Right. Li is equal to exponential, I'm going to write it this way, multiply by 300. So the value of the exponential is going to be somewhere 0.179. So exponential of 0.179 times 300 is going to give us the value of L, the final length, and that's going to be 0.179 times 300. It's going to be 358 millimeter. So it's going to be 358.806 millimeter. Now the delta L will be the difference between the original and the final, which is 58 point. So delta L here, delta L will be the difference between, since we know delta L is difference between the final, which is the final length, sorry, final or instant length minus original length. So we know this is 358 and this is 300, so the result is going to be 58 point. Millimeter. Now remember, things is easy in true stress, but you have to know what you're doing. Do not mix the cases together. If you have a known case, you can use this one to find the value of k and n. Then you're going to use the equation k and n constant. You can use it to find any other possible cases we have it there. Now I'm going to solve one more example, which is relating. This is 305, yes, exactly, and this is delta L will be 58.8 millimeter. So we're solving another example. Let's see if I have for chapter 6 which one to solve it again. One which is relating an engineering, so engineering stress, engineering strain with the true stress, true strain. I'm going to solve one because we may have this case also the exam. Now let's see. Okay, I'm gonna solve 6.45. 6.45, we have it here. So this is 44 is easy. 45 is the one that kind of exam question. So I'm gonna tell you here what do you expect for the final as well. Now, instead of for a brass alloy, the following engineering stresses produces the corresponding plastic engineering strain prior to necking. Now, two things we will understand from the sentence here. First, plastic or prior to necking, it tells me you are in a plastic zone. This is first. Second thing that I'm understanding here, they are engineering stress. They are not true. So they are engineering stress and corresponding plastic engineering strain. So those are engineering strain, engineering stress. I cannot use them in this equation. I cannot use them for the equation of true stress. Remember, this is one thing. That's why I'm going to explain this one to you, to understand that if they are engineering, you cannot place them inside this equation. So those are true. And you know that there is a relation between engineering stress, true stress. There is a relation between engineering strain and a true strain. So if I want to find those two, I have to convert them. Now, you say on the basis, let's see what does it ask the question. Those are given, yes? On the basis of this information, compute the engineering stress necessary to produce an engineering strain of 0.25. Now, the beauty of this example, this problem, is that you are in plastic zone. In order to work in plastic zone, this is the main equation that you have there. Why? Because Hooke's law does not work there. And engineering stress, if I want to find engineering stress, I know engineering stress is force over area, yes? We know this one, engineering force over original area. I don't have original area, I don't have force, so I cannot use this one. I cannot use Hooke's law. I've seen students, they use this one. This is only valid in they say, okay, let's use this. Yeah, they say, okay, this is brass, let me go and take brass modulus of elasticity, and I have this strain, I found the stress, and that's it. No, that does not work as well. Why? Because you are in a plastic zone. Hooke's law does not work in plastic zone as well. Poisson ratio does not work in plastic zone as well. So you cannot use those information in plastic zone. So how would you solve this one? But you have to use this equation in order to get to these things. So you cannot directly find engineering stress for this engineering strain. The mediate between them, it's this equation. So you have to convert, or you have to find the true stress, then you can come back to engineering stress. So I'm gonna, let's see if I have, I can just simply draw a table here. Now I will make a table here. Let's make a table black. No, it's too long. Just it's explaining it. Okay. Now we have three cases here. 1, 2, 3. We have three cases that we're gonna explain here. Now at the top, let me just add some more information. Now let's say I'm trying to write down, this is sigma, a true stress. There will be a true strain here. There will be a true strain here. Then there will be an engineering stress and an engineering strain. Then I will write delta, if I need delta L, or what else, there is L, I have it, L will be the same, say delta L. Those are some information that I will explain it why, because normally asking question like this in final exam. So there will be a question this manner. So you know what you're doing. You don't need to make this table. I'm making this table so the student will understand what do we have here. If you make this table, you will not make any problem, or at least you know what you're doing. Now, it says that an engineering stress 235 megapascal. So let's say I'm taking this one as a case 1. This is case means that 1, 2, 3 means that I have some information. Some points on the curve, I have information. Remember, this is a point on the curve. 235, I'm not going to write in a true. This is here. So I'm going to write this one here. That's going to be 235 megapascal. I have here, this is an engineering stress, and I have the corresponding engineering stress, so I'm going to write it under here, which is 0.194. Now I have another case. It's a 250, it's still engineering stress, so I'm going to write it here, 250. Then the corresponding is 0.296. Oh, this is megapascal as well. This is megapascal. Now I gave you a task. I told you that to find n and k for me when you had 4 values: 2 sigma true, 2 true stress, 2 true strain. Now the mistake, I've seen it, I'm going to explain this one as well. They directly use those 4 values to find n and k. Remember, I cannot use them. I'm always saying, student, create this table if you don't know what you're doing. If you know what you're doing, no need for this table. So those are not true. I cannot find n and k. If I want to find n and k, I have to have 2 true stress, 2 true strain, which I need to fill those 4 empty cells here. Now, how do we convert true stress to engineering stress to true stress and engineering strain to true strain? By using the equations that we know. So the equation that we have it, let me write them somewhere here. We know that sigma true is equal to, if I'm not wrong, engineering stress, or true stress is equal to engineering stress 1 plus engineering strain. And I know that if I want to find the true strain, it is equal to ln natural logarithm of 1 plus engineering strain. Do I have engineering strain? Yes, I have them. Do I have engineering stress? I have them. So I can simply find those four values there. Now, let's find, first I'm gonna find let's find the true stress. For the first case, 235. So for the first case, I'm writing it. For the second case, I'm not writing it. I'll just directly get the answer. So I have 235, 1 plus the engineering strain, which is 0.194. 0.194. So through here, I can calculate the true stress, which I'm going to write it here. Let me give them a different color so we know that we found those by using calculation. So 235, 1 plus 0.194. So I have 280.59. Those are megapascal. I'm not going to write the units. I can write directly at the top of it, so it will be easy for us. This is megapascal. Megapascal here. You don't need to write every time the units. Now this is 1. I can calculate the true strain by using ln 1 plus 0.194. Sorry, the 1 is supposed to be, oops, everything is gone. It's not bringing it. Okay, 1.194. So I can find this one and type this one back again here. It was 280.59. So if you calculate this one, you're gonna get the true strain as well. 1 plus 0.194. We're gonna get this one to be 1.17731. I'm not writing it as 4 or 5 digits, that is to be accurate. Now I can convert the second one as well, the second one by using the same equation that I had it here. Let me write back this equation. True is equal to engineering. What's going on? This is engineering 1 plus engineering strain. I'm going to use the same equation to find the other one, so I'm typing directly. Now if I have the four values, I'll be able to go and calculate n and k value. So 1 plus 0.296, we're going to get here 324 megapascal. For the other one, we're going to use ln 1 plus 0.296. It's going to give us 0.25, 0.259. Let's make this one 28. I have it here. Those are now four values. I have it for the true. Then I can find value n and k. You know how to do this one. I asked you to do it for me. So I'm directly going for the values that it's basically here. So this is what we do, 280, and this where we convert them, and the true strain as well, we found them already there. Now you're going to use whatever the things that I told you to do with there. You're going to find n and k value by the, remember which one you're going to use it. You're going to use the four blue values, not the red one. The red one are engineering. You cannot use it to find n and k, so you have to use the blue values here, which after converting those to the true, we use those true to find the n and k. So from those four, you found K and N. So let's say I have the K and N, I'm writing it somewhere here. Remember, by K and N, it's constant for all of them. So we have K and we have N. They're constant. I'll make sure for all of them are the same. So K found to be 543, and for N, remember N always must be smaller than 1, so if you made a mistake you know it from there. So I have N and K. Now I can go and answer the question that we have. Now the question, let's come back to the question. The question, what does it say? I'll just clear some board. This one we don't need it anymore, so we know what we did. Now, the question says that find an engineering stress necessary to produce an engineering strain of 0.25. So this is the third case. The third case, what do I have? I have engineering strain again, 0.25. So I have a value which is given here, 0.25. What is required? Sorry, make this one red, so we know it's given value. A 0.25 engineering strain is given. What is required? It requires to find an engineering stress. I cannot find I don't have relation between this and this unless I have the values here. Now, if I have a true stress, look, if I had a true stress, I would find engineering stress easily, yes? Because I know that the relation between those, we know the relation. I can use this relation, 1 plus engineering strain. This is the relation that the only way that I can find this engineering stress is through this equation. But I need what? I need a true stress. Now, I'm sorry in the beginning I didn't told you why would I need to find N and K. I told you it's necessary. Why? Because we're in a plastic zone. But the reason is what? I need to find a true stress here with an engineering. Look, this is for the third case. Remember, I'm trying to look for the third case. Remember, you cannot use those anymore for the third case. You are in the third case, you have only this value. You only have this value. And you want to find this one. This is what you're looking for. But this one here, it is unknown. So if I find this one, I can find the engineering stress which is required. How can I find this true stress? The only way is here. The only way that I can find true stress is by this equation. I have K, I have N, but do I have true strain? I don't have true strain again. Can I find this true strain by using the equation that we know, the relation between? So we know that true strain can easily be found by just knowing an engineering strain, because the relation between them is ln 1 plus. So true strain is equal to ln 1 plus engineering strain. We know this one. Now, I have 0.25. It means that I can convert this 0.25 to a true. So I can convert this one to true. Then I can use the true strain with the N and K that I have them to find the true stress. Then I can bring the true stress inside here with this engineering strain. Then I will find the result or the question or the required part that I have there. Now you realize that this is the hardest question that we have it in plastic zone. When we have engineering stress, engineering strain, and question will be asked in this manner. So the first one will be what? The first one that will be used is this one. So we're going to use this equation y. Remember, I'm talking about for the third case. The first and the second case only required to find N and K. Remember, nothing more. Those two I told you before, if n and k, and now when you need 4 values, I mean true, 2 true stress, 2 true strain to find them. That's it. We're not going to use any those information for anything else. We just use them to find n and k. Now, our work is on the third case. We have an engineering strain 0.25. We want to find the engineering stress, but we say we cannot directly find it, so we have to use indirect way. The indirect way means we have to find the true stress, true strain, then we can come back to the engineering stress there. So we can simply convert an engineering strain to a true strain by using this equation. So ln 1 plus 0.25. So ln, this is ln 1 plus 0.25. I'm going to convert this one to, so ln 1 plus 0.25. That's going to give me 0.2. It's going to make this one blue. So we found it here. That's going to be, remember I found from this one, so I can, there will be a lot of lines, but if you're watching the video you know what doing. So this equation is going to give me, sorry, let's choose different color. So this one is going to give me the result here. Which is going to be 0.223. I'll go 14 as well to be more accurate. Now I found this one. Then I can use this equation. Because I have K, I have N. Now I have a true strain. I can find a true stress. Now, writing down. So let me just write somewhere here. I'm going to write it down. A true stress, because I want to find a true stress for what? For a condition when I have a true strain. So K, we already know it, 543 multiplied by, do I have a true strain? Yes, 0.22314 to power n. N we have it, which is 0.383. Now through this equation we can get the engineering, so the true stress, then we can use that true stress with this equation with the engineering strain to find the engineering stress. It's a bit tedious, I know the board, because I don't want to delete these things, at least to know the relation between them. So if you follow the things that I told you, you'll be able to understand what we're looking for here. 383. So we're going to get 305 for the result here. Let's begin 305.707 megapascal. Now this is true. We don't want this one. We need the engineering strain. Now I can explain why we need all of these things. Remember, the question was asking an engineering stress. Since we are in plastic zone, this is the summary of the question. Since we are in plastic zone, I don't have a way to find engineering stress or engineering stress unless by using the relation between true stress and their engineering, or the relation between the true and the engineering. So that's the only way that I can find engineering things from there. And if I want to find this guy here, this is the engineering strain for an engineering stress. For an engineering strain, which is 0.25, I need a true stress. Now when I said I need a true stress, that true stress must be corresponding to these values. I cannot use this is a true stress. The student say, okay sir, you said in the class that we need a true stress. This is a true stress. Yes, sure, it's a true stress. But this true stress, it has a true strain, it has an engineering strain, has its own engineering stress, engineering strain. I cannot use this one. That's why I'm saying that the table is going to help you. So I have to find a true stress for this 0.25. Look, think of this way. This 0.25 engineering strain, I have to find the true stress for this one. Now this, I can convert it to engineering. This I can convert to a true strain because it's engineering. I can convert to true strain. In order to convert true strain or to find the true stress from true strain, I need to use this equation, which K and N require. We said that in order to find N and K, so K and N, I need 4 values. Those 4 values, 2 true stress, 2 true strain. I don't have any information on 3, so I'm going to use the 2 cases given here. Those are engineering stress, engineering strain, so I have to convert them to true stress, true strain. Then I can use those 4 values to find K and N. Then I can use this true strain to find the true stress. Then I can use the true stress with the engineering strain to find the engineering stress. So this, the procedure here, it's kind of long solution. So I'm going to remove this part here. I will leave the table there. So I'm going to look at the solution that it has this. So we said that first we convert those two. 280, they made it shorter, 280, 300, I don't know, there must be with a 0.6, should be here as well. Now we said that we convert those two to a true, the 4 cases, then the N and K found, then you're going to continue. We have that 0.25, we're going to convert it to what? So now converting this engineering strain to true strain, that's going to give us 0.223. Then using the equation, so the only way that the corresponding true strain will be used with the equation we have it. I have K, N, then we have the true strain, 0.223. Then we found 306. They made it approximately 306. I made it 4-digit win, so that may be accurate. That's the answer there. This is a true stress. Then using the equation that we know that the true stress is equal to engineering stress times 1 plus engineering strain, and that's going to give me a 245, which I don't know, I didn't find it. Yes, no, I don't know. I believe I didn't find the values here because I have this one now. I have this one, bring it there with the 1.5, you can find the final answer will be 245 megapascal. Now this is the hardest case. Now what do I do in the exam? Sometime I make it easy for student. But why? I wanted to know if they understand. Look, sometime I'm giving 2 cases here. So I'm telling student, okay, I'm giving this one to you, this one with those 2. What is only, I don't need those 2 years. I only convert those 2 here, then I'll find the N and K. Instead of giving you 4 engineering, I will give you 2 true. Maybe I will give you 2 true, 2 engineering. The engineering will be converted to true, then the 4 true will be used to find N and K, then I can go for answer the last part. Or I can give you delta L. If I give you delta L, what does it mean? If I give you delta L and L, what does it mean? It means that I gave you engineering strain, at the same time I gave you true strain, remember. So if I give you delta L and L, it means that I gave you the engineering strain and the true strain. Why? Because we know that engineering strain is equal to delta L over L. Now how do those two relate to engineering to true strain? We know that true strain is equal to ln natural logarithm of instant length over original length, which is this is L0 here as well. Now, L0. Now I know that this guy here, the L0, this guy, it's nothing, just L0 plus delta L. So if I give you, those will be the L0. If I give you delta L and L, it means that you can simply find the true strain and the engineering strain and the true strain. So instead of this, I can give you those values. Remember, nothing. I can just simply say, okay, I gave you this, find the other one. Remember, the relation between those two, you have it. The relation between those two, you know them. Remember, the relation between those two are N and K required. The relation between this group with this group, you already know them. Why? Because this is the relation between the engineering, the true, and there's a relation between the true. But I don't have relation between the engineering here because I am in plastic zone. I cannot use Hooke's law. I cannot use Poisson ratio. I cannot use the other equation unless I have information. But mainly will not be given. Why? Because in plastic zone, only those information will be given to you. So remember, question like this, it's appropriate for final exam. I believe that will be enough for this chapter. There are some other questions that you can go through them and solve them to see how we'll be able to do those. There are some others. I recommend you to look at them, because maybe some of them, I don't know. Just read them to see which one is hard for you. Try to. Now there is one question I want you to practice it as well. That's going to be 6.24 and 6.2324. We asked them several times in the final exam. We asked them in the final exam, so I need you to know them. If I ask a similar question really similar to them, remember, since it's in an open book exam, I'm not asking exactly the same question here because you already know the solution is available, so students just simply typing it. So I have to change the question, but remember, I'm not asking something that I haven't explained it. So it will be something that you already know. If you understood, then you'll be able to solve the question for me easily. Thanks for watching.